Year 11 IB. Today we're looking at applications of exponential functions. And the first example we're looking at here is exponential growth, and then the second part of the section looks at exponential decay. So exponential growth is where we see the growth of any sort of populations, be it people, bacteria, anything where things are multiplying. So here in the example from your textbook, we've got 100 mice under favourable conditions. They're increasing it by 20% each week. That means, remember from your percentage work in years up to year 10, that if it increases by 20%, then they're multiplying by 1.2. If P is your population after n weeks, then at the beginning, P0 is 100, the original population. So P1 is going to be P0 times 1.2, P2 is P1 times 1.2, and so on. And we see this pattern where we're multiplying by our factor of 1.2, and after 3 years, it's been 1.2 cubed. So we're obviously going to come up with our formula of 100 times 1.2 to the n, and n is going to be greater than or equal to 0, because we are taking a P0, which is our initial population. So when you graph that, here's our exponential curve, like we've seen in our previous example. Note in this case, our y-intercept, which is our population, is at 100, which is when n equals 0, and that's that multiplier, like that a value, is causing that to be at 100. So our general equation we've been looking at is a times b to the power of x minus c plus d. So that was our general type of exponential function. So what sort of values can we have for our a, b, c, d's? You might like to pause the video and have a go at putting some domains or for that, sort of particular values for these parameters. So remember the term for these A, B, C, D's are parameters because they're affecting our equation. Then that X and Y are the variables. What values can these parameters have? So pause it, have a go, and then put it back on. Alright, so an easy one to start with is if we want our graph to be increasing like this, that means our B value has to be, or not, it's got to be positive. We don't want it equal to 0 because then we wouldn't have an exponential function. And remember, we don't want that equal to 1 because 1 to any power is just going to be 1. Now, how about a, that multiplier at the beginning? Can that be a positive number, or can it be a whole number or a decimal less than 1? Yes. Do we want it negative? No, because if it was negative, that would flip our whole graph downwards. And we don't want that. Alright, so we'll get rid of that option and we'll just go a is greater than 0. I don't know if we think like that again. Obviously we don't want it equal to 0 because we won't have a function, and it doesn't matter if it's not so steep or steeper. The C, that's our shift, that's our horizontal shift. Does it matter if that's shifted left or right? No, it doesn't. So we can have any value. It can be positive or negative. So that's just going to be any element of the real numbers. And what about D? We want it increasing. The question is, could we have it starting at a negative value? Maybe we could. I don't know. In a real situation where we're applying this, we don't usually use much on the negative scales down here or down here. We don't usually talk about some negative time, and we don't talk about such as a negative population. So, yeah, so generally that is going to be greater than 0 or equal to 0. Obviously, if it's equal to 0, it's not adding anything. All right, so here's our example. We've got bacteria of a particular weight, W, in a culture after T hours of growth. It's given by W equals 100 times T to the 0.1 T grads. What's our initial weight? Initial meaning we're at time equal to 0. So our weight is going to be 100 times 2 to the 0.1 times 0, which means we have 100 times 2 to the 0, which is 1, which is 100. So that number is our initial conditions. If we want to find the weights at particular times, then we're just going to substitute it to our equation. So if we want our population as a function of time at 4 hours, we've got 100 times 2 to the 0.1 times 4. Into your calculator and bring up 132 to 3 significant figures. Our weight at times 10 is going to be 100 times 2 to the 0.1 times 10. You can see that becomes 2 to the power of 1, which is 200. So this is actually the time to double the population, or double the weight. Populations in this one. So in 10 hours, the weight of bacteria has doubled. If you do a quick sketch, then it's going to be increasing like this. This is our 100, and what we need to scale, here we go at 200, so that must be 10 down here is 4 time weight. All right, so that's what your graph would be looking like. The next part of the question is saying, when will the weight be 225? So what we're doing in this case, we want to solve 225 equal to 100 times 0.0 times 2 to the power of 0.1 t. Now at the moment you can't solve that algebraically. Eventually next chapter you'll be able to do this with logs. But at the moment you're going to do it with a graphical method. Which simply means on your graph, draw in your 225 and then read off down whatever the x value is. So you want to put in this line into your graph. So I've done that on your software with the Inspire, and we come up with that graph. So the point of intersection here is telling us at what time we end up with that population. So at time equal 11.7 hours is our answer. So you need to be able to put in your first function as given in the equation. The second function is the time, is the weight we're looking for, and get your point of intersection. So coming back here, I can put that in here. The time equals 11.7 hours. Right, so that's exponential growth. Exponential decay is simply the reverse situation. So it could be something like radioactive substances. It could be, say, bacteria, antibiotics acting on bacteria, reducing the growth. It could be exponential. So your graph is basically looking like this. And again, remember, if we're talking time, then we're not really looking at this part of our graph, and we may not, this might not exist either. But definitely if that's going to be time, we won't be looking at negative time. Unless you're going to think back, well, what time would it have been? Then that negative time is meaning the time before you started. Can you remember now what sort of B values we need to get our curve going down? Hope you might, of course I remember. We're going from values from 0 up to 1. The other situation is where we have y e to the minus x, and we've got b greater than 0 and not equal to 1. Alright, so having a negative x is the same as having that decimal or fraction less than 1 as the base. So, in our example, the decay of radioactive substances, the initial mass is 20 grams. It decays by 5% per annum. Find the weight after 10 years. So we do the same, think through the same process that we did with the exponential growth. You might be able to go straight to a formula, but if not, step it out and work it out. All right, so our initial weight is 20 grams. After 1 year, because it's decreasing at 5% per annum, it's going to be 20 times, if it's decreasing by 5%, it means we only have 95% less. So we're multiplying by 0.95. After 2 years, it's going to be 20 times 0.95 times 0.5 again, so that makes it squared. So this, after 2 years, they're matching. Right. So therefore, our equation based on t is going to be 20 times 0.95 to the t. So always look carefully at your equations to see what time it's at what value. And you'll come across questions like that that get a bit confusing. If we want the weight after 10 years, so that means 10 years have passed, then we want 20 times 0.95 to the 10, and then putting that into your calculator. All right, pause that for a moment and see. Hopefully you came out with 11.97 for that. And this one, we've got to do that one. We're coming out at 19 for there. All right, just work those out on the calculator. So I'll put 19 from after 1 year, up to 2 years. It's now 18.05. That was our equation, our general one. Remember that t is greater than 0 or equal to 0. We come out our mass at time 10, 11.97 grams is what it's decayed to. Sometimes you talk about the half-life of radioactive material, like how long it takes for it to decay to half the amount. So if we wanted this to come down to 10 grams, because initially it was 20 grams, then we're doing that same calculation as we did earlier. 10 is equal to 20 times 0.95 to the t. So as I said, you could put that into your calculators where you've got, this is your first function, the second function to get the intersection. Or you could actually divide by your 20, so you're getting 0.5 is equal to 0.95 to the t. So do that division by 20 to get 10 on 20 is 0.5, and then put this in your calculator. Otherwise, when we come to looking at logs, and I'll put this in now so that when you get to logs, you'll recognise this as you study your notes, t will also equal log to the base 0.95 of 0.5. Anyway, that won't, if it doesn't make sense at the moment, if you haven't ever seen logs, don't worry, we'll spend a whole few weeks working on that. At the moment, not too concerned. So, when you graph that up, I did a graph of 20 times 0.5 to the power of x, and our second function is equal to 10. Here's our point of intersection. Remember, it's the x value that we're after. So it happens at time t equals 13.5 hours. So I think it was hours, not days. Years. So it's going to be a slow breaking down. So that's years. So therefore, we come back here, I'll just put the answer on the other page. There. So our time equals 13.5 years. Right, so hopefully you've got a better understanding of how we can model exponential growth or exponential decay. So have a go at the questions now, and we'll have a go at those in class. Thanks for listening, and we'll see you tomorrow. Bye for now.